Welcome, this is lecture number 29. In this lecture, we are going to talk about derivation of small signal transfer functions. So, in this lecture, we are going to first recapitulate our AC small signal model of ideal as well as practical DC-DC converters. Then we will derive various small signal transfer function, and then we try to understand what is output impedance, what are the practical limit, then what is the control to output transfer function, then what are the bandwidth limits. So, we will try to understand some of the aspect in this lecture. So, first we will consider small signal transfer functions of a synchronous buck converter. So, we have already discussed multiple times in the past that if we take a synchronous buck converter, this is the ideal synchronous buck converter, in which this is the controllable switch and this is the complementary switch and this is the gate signal. The Q is the gate signal. So, if we recall that our large signal AC equivalent, large signal that equivalent circuit model, this buck converter can be ideal buck converter can be represented by this, okay, and this is the input voltage. And why it is large signal? Because we are considering both the part-up term as well as the DC term, right. So, it consists of both AC and DC, and we have discussed in the past that this circuit can be used to we can carry out DC analysis as well as AC analysis. So, in the previous lecture we have already completed the DC analysis. So, in this lecture we are taking this model and we are considering the AC equivalent circuit, and in order to get the AC equivalent circuit, the first thing we will replace, because this voltage source, if you look at this is a sum of a DC component plus AC. Now, we can substitute all the DC component to be 0. So, that means the voltage source will be shorted and current source will be open. Another thing you will notice that if we consider this current source, this is a dependent source, this is in parallel with the voltage source, and since it is parallel with the voltage, that is the input voltage, this has no meaning, that means it has no role. So, we can simply drop it. So, we are getting this is the AC equivalent circuit. So, in this circuit we are all talking about the part-up model, where this is the inductor part-up model, like as it is, the inductor, capacitor, resistance, everything is there, and this is the DC transformer, the step down ratio 1:D, and this circuit we are going to consider this circuit to derive various transfer function. The first thing we want to do, derive input impedance. Now, we are all talking about the open loop buck converter, where there are few things, that means the duty ratio. If we consider duty ratio, so we are giving a fixed duty ratio, that means in this case we are talking about duty ratio equal to D. So, the D tilde in this case should be 0. That means in order to derive input impedance, we have to set the duty ratio perturbation to be 0, but it does not mean there is no duty ratio, because it has a fixed duty ratio D, but the perturbation is 0 because it is under fixed duty ratio operation. We are also not considering this perturbation with this output current, because this is used, it is an external sinking current, it is used to derive output impedance, but here we are considering input impedance. So, we can disconnect this particular path, okay. So, there is no current and the current source should be open. So, that means we have removed this path, and we have another thing, since D perturbation D tilde is 0. So, this term will be 0, and that means we will short this path, and this is exactly what we have shorted this path and we have opened this path, okay. So, now if you look at this circuit from this perspective, right, as if we are viewing from here, so as if we are giving an input excitation. So, you can think of, that means if you have a laboratory power supply, okay, you want to check the input impedance. So, this is like your DC power supply, and this is connected to a resistive load. Let us say it is a resistive load, and what you are trying to do, you are actually applying an AC excitation in the input voltage, right. Again, it consists of both DC and AC, but we are only considering the AC excitation. So, this AC excitation input perturbation, if we apply, and of course input current also if we measure. So, if you measure AC input voltage, the AC term, and the AC that input current component, And then if we carry out that frequency response analysis, that means if we sweep the frequency of excitation, then we can derive this input impedance, right? And what does the input impedance indicate here? It is like L in series with the RC parallel branch. That means it is nothing but, if we take this particular branch, so that means here you can see SL is there and it is in parallel. So, what is this branch? If you take this to be, let us say Z1, so Z1 is nothing but 1 by Cs, that is the capacitor in parallel to the resistance, and if you derive, then you will get this part, okay. And this is added with the inductor impedance, which is this part, which has SL term. And since this impedance, if we take it to this primary side and there is a turns ratio 1:d, then we have to divide 1 by d square, right, because it is an impedance, right. So, it is a turns ratio square, and that will give you the input impedance. That means the input impedance of a buck converter is nothing but, if you take the frequency dependent term, right. So, it is an ideal buck converter. The input impedance has two zeros right here, the impedance, and one pole, because it is an impedance. So, do not worry about this improper transfer function, because it is an impedance, right. So, this input impedance, if you talk about the low frequency behavior, that means if you take S equal to 0, then what you will get? That means you will get simply R by d square, you will get R by d square. So, this is the input impedance of an ideal buck converter at low frequency, very low frequency. In fact, this impedance play a significant role when we want to, let us say it can be buck or boost, any other converter. Suppose we want to connect to a solar panel because we want to do maximum power point tracking, or we want to extract maximum power. So, we need some kind of impedance matching, right. So, then we have to adjust the duty ratio in order to match the impedance, right. So, in this case you can derive the same thing for a boost converter, and because boost converter is generally used for extracting maximum power from a solar panel, because the boost converter input side you have inductor and the current is continuous, right. So, I am just saying that how to derive the input impedance, and this input impedance play a significant role in terms of impedance matching in the source side. When you connect another source to this converter, it plays a significant role in the design of input filter, because we have already I think we have already discussed in the previous lecture that in past lecture, I forgot exactly lecture number, where we talk about the impedance analysis. So, we have used the Middlebrook extra element theorem to identify the stability criteria for series connected converter, right, or when you put on filter, then how do you justify stability? In such cases, the input impedance play a significant role in the stability of the converter, right. Now, we want to also talk about output impedance. So, if you talk about output impedance now, again we are talking about the open loop output impedance, where we are applying a fixed duty ratio gate pulse. That means our duty ratio again will be set to D, capital D steady state, and D delta equal to 0, right. So, again this term will be 0 and we will short this path, and here we are not talking about any supply perturbation. That means there is no supply perturbation. So, if there is no supply perturbation, this term will also be 0, and if it is 0, this is a voltage, so you have to short this path. So, in order to find the output impedance, you have to short this path, because we are taking perturbation in the input voltage to be 0, and any 0 voltage is nothing but the shorted path, right. And similarly, since the duty ratio perturbation is 0, this is also shorted. So, now we want to find out the output impedance, as if we are looking from this side, again as if we have taken a DC power supply, okay, and this DC supply is connected to an external load, right. So, it is connected to an external load, and this is my I0 sinking load, and again I am talking about the AC excitation. That means it will have DC term, but we have to separate out the DC term. Now we are trying to measure the output impedance by looking from this point. That means basically it is V0 by I0. Since it is a sinking current, it is minus V0 by I0. That is the output impedance, right? So in order to derive the output impedance, you will find since it is shorted, so this will resemble like if we short this path simply. That means this will represent something like inductor in parallel to a capacitor and a resistance, and this is connected to your external current source sink. So this whole branch is actually representing your output impedance, right? So LCR, but if you do not consider resistance to be the part of the converter, then it is just LC, but we are talking about a ideal converter. In a practical converter, we will have a parasitic of the inductor, parasitic of the capacitor. They will play a significant role in the output impedance. So that means it is a parallel combination. That means it is written as the output impedance is written as SL parallel 1 by CS parallel R. So this is the branch, and this can be derived like this, right? That means at very low frequency, if you set S equal to 0, that means the low frequency behavior. If you say the low frequency behavior, that means Z0 0 close to 0, this will be simply 0. That means you can view from this circuit. That means if you take this RLC branch at very low frequency, this inductor will behave like a short circuit, right? Very low frequency DC. Capacitor will behave like an open circuit, right? And that means you will get something like a shorted path in parallel to a resistance, and that is your external current source, right? So that means this will be like a 0 output impedance, right? At very high frequency, the inductor will become like an open circuit and capacitor will become like a short circuit. Again, it will be 0. So that means in an ideal buck converter at very low frequency and at very high frequency, you have almost 0 output impedance, but in the mid range, you will get this dynamic effect of the frequency dependent term. But in a practical converter, you will see it will not be 0 at very high frequency, neither it is 0 at low frequency. So it has some finite value. Audio susceptibility. So audio susceptibility means we are talking about if we apply some perturbation in the supply input side, we want to see what is the effect in the output, and this is particularly important because any power supply, we want to see, we know about something called power supply rejection ratio. Power supply rejection ratio. That means if there is any disturbance coming from the supply side, whether our output converter is able to totally attenuate that effect in the output or not, or is it going to get propagated to the output side. Here we are talking about the open loop DC-DC converter. Definitely this open loop converter, this will be propagated, but once you close the loop, we want to make sure that it is one of the control objective that we want to reject the disturbance due to the supply voltage. That should not appear in the output voltage. So the first is that the converter in open loop, so the deperturbation to be 0, that we have discussed. Here we are not talking about output impedance, so external current sink is also 0, that means that branch is open, and that means this will be 0, and this circuit will look, that means we have a supply disturbance and we want to see the effect in the output voltage, and this path is eliminated, this is also shorted. And in all cases we have eliminated this branch which was there earlier, which was like a ILD term, because we discussed this will have no meaning because it is already connected across a voltage source. That is why you have eliminated. So that means we have removed this path because this has no meaning here. Okay. Now we want to derive this audio susceptibility, and this can be derived by taking again this branch impedance and then the output voltage, that means if this is Z1, so output voltage will be Z1 by Z1 plus SL, this whole, into what is the voltage across this path. So, this will be V in by into D, sorry, V in into D, that means, yeah, it is V in into D, right. So, V in into D, this term, okay, and this impedance. So, it will be D into V in hat. So, from here you can find out this expression, okay. So, this is the expression of the control 2, and you see at very low frequency the audio susceptibility is simply equal to D. That means it is nothing but D into V in, and which is consistent with the buck converter relationship. That means, if there is any disturbance, low frequency disturbance at the input supply side, it will be propagated to the output side by multiplying a scaling factor. That means, at very low duty ratio operation, this effect will be small, or it will be, the effect will be negligible, not negligible, I think it will be low, but if the duty ratio is high, then that effect will be propagated to the output side like a substantially, it will be propagated, right. The another part, which is one of the most crucial part, because what we have discussed so far, audio susceptibility, input impedance, output impedance of an ideal buck converter, but in reality we are going to control the converter. So, for controlling the converter, the most important transfer function is the control to output transfer function, because if we understand this control to output transfer function, then by means of closed loop control, we want to achieve some desired output impedance, some desired input impedance, some desired audio susceptibility. So, this is one of the most important. So, here in order to achieve control to output transfer function, we will simply set this to be 0, there is no supply disturbance, and we will also not consider any output perturbation during the process of derivation of control to output transfer function. That means, the circuit, it will be shorted and this path is already open. Now, we need to find out the transfer function of this, and since it is already shorted, so this you can short here, right. So, you are talking about this particular circuit. That means, if you want to find out the control to output transfer function, again if this is my Z1, so my V0 hat will be Z1 plus Z1 SL, this whole thing into V in into D hat, right. So, we want to get V0 by D hat, and if you do that, you will get this transfer function like this. And you will find here in the control to output transfer function, in the like a DC gain, that means if you take GVD DC gain, this is simply input voltage. That means, in this case the DC gain is nothing but the input voltage. That means, if there is any variation in the input voltage, your DC gain is going to drastically vary, it is going to vary, because it is input voltage dependence, okay. So, this makes, that means if you want to control this converter by means of direct duty ratio control, then this is one of the problematic, like input voltage dependence in the DC gain, and in order to reduce this effect, you can consider input voltage feed forward in order to do that, and that we have already discussed. So, that means small signal transfer function of a buck converter, we already talked about output impedance of the open loop buck converter, we already talked about the control to output transfer function, we already talked about audio susceptibility, right, if we talk about from V in to V0, and if we talk about input impedance also we can consider, right. Now, you will see the output voltage perturbation here, it is the sum of all these. That means, if you write down, okay, so that means if you write down V0 tilde, it is nothing but GVD into D tilde plus GVG into V in tilde plus, sorry, minus, because there is a negative sign here, minus output impedance into I0 tilde. What does it indicate? That means if you do not consider any change in input voltage or load current, that means a positive change in step in duty ratio, your output voltage should increase. Similarly, a positive change in input voltage, your output voltage should increase. But a positive change in load current, the output voltage is going to decrease. And in an ideal converter under steady state, again it will come back, but this negative effect will come like a undershoot behavior. But in a practical DC-DC converter, we will see the output voltage will get shifted. I mean, it will slowly reduce if we increase the load current, because this is because of the, you can think of a, if we talk about, we have discussed in I think lecture number 19 that a practical voltage source, if you take a series resistance in internal impedance, that means as you draw more and more current, then the drop across the resistance increases, as a result the voltage also decreases. So that means this is the input impedance we have discussed, this is all ideal converter. Output impedance also we have discussed, and audio susceptibility, and then the last one is the control to output transfer function. You will see in output impedance, audio susceptibility and control to output transfer function, the numerator polynomial, that means the poles are common, they are same. That means it is like a delta S, which is common for all, here, here, as well as you can see it is here. Input impedance is different because its dimension is also different. So that means there is something like these poles will have a significant role in all these three cases, like, and of course it will also affect the input impedance, but we generally do not talk about input impedance unless we talk about input filter or more converter connected to the like a input side. Otherwise, for a single DC-DC converter, if you are only talking about load transient performance, you know, for I mean, if we assume that your converter bandwidth is not affected by the input filter, then we can simply analyze the transient recovery and everything by simply these three transfer function where the poles are common. So, the poles play a significant role, right. Now, if we talk about a practical converter where we are considering the on time resistance of the switches, the two switches, the DCR of the inductor, ESR of the capacitor, then we already know about the equivalent circuit. So, we know what is Re equivalent, it is nothing but the on state resistance of the switch plus RL, and we are assuming the on state resistance of these two switch, they equal to R on, that means they equal to, this is like a R on. We are taking more or less same, although there can be slight difference, but still this is applicable. So, this is a R equivalent and this is a ESR, and we have already discussed about this equivalent circuit model. So, we are only taking the AC equivalent circuit where we have dropped this term, there was one extra term was there which was IL D hat, we have dropped it because we have ignored this, because it is connected across a voltage source. So, it does not make any sense, because if you connect a current source in parallel to a voltage source, then that whole network behavior will not be affected. That means, in the analysis we can simply remove the current source, okay, for the AC analysis. Okay, so all these cases. Now, input impedance, the same method that we discussed, only with parasitics, right, and what we will see, the circuit simplifies to this. So, this is the input impedance where this is Z in, and this term if we take it to this side, that means I am telling the whole thing like a Z1, this whole branch as a Z1, and if you take it, it will be 1 by d square, because there is a step down ratio, right, and then you can obtain the input impedance expression from here. And this input impedance can be shown here, it is nothing but this expression, where the alpha is nothing but R plus Re, that is your R equivalent, divided by R. So, generally it is greater than 1 if Re is greater than 0, but it can be approximated to 1 if R is very greater than Re, right, and generally that is true because your load resistance should be higher than the equivalent resistance. But suppose we are talking about a very high current application, low voltage high current, where the load resistance itself is very low because your load current is high, and you have chosen an inductor as well as switch where the equivalent resistance can be comparable with the load resistance, then this alpha will have a significant effect. Okay? But generally the design thumb rule is that our load Re should be small, but that poses a constraint because if you want to find an inductor with a very low DCR, right, if you want to reduce the DCR significantly, then you have to pay more price, right, for a low DCR inductor. Similarly, if you are talking about low RDS on switches, then you need to figure out that, because the transistor there is a figure of merit, right, FOM in a MOSFET, which is generally RDS on multiplied by QG. That means on state resistance multiplied by the gate charge. So, generally if you want to select a MOSFET with lower RDS on, then it may so happen that you will end up with more QG. So, if you operate at a higher switching frequency, then a switching loss will increase due to this QG. Okay, so that means we have to select this component very precisely about how to select MOSFET, inductor and so on. But what I am trying to show here, even if you select some MOSFET or inductor, and if you can extract the value of DCR on state resistance from the data sheet, then you can obtain the output impedance, input impedance from this expression, right. So, all these parameters, the poles, zeros are given here. Okay, now what is the significance of the input impedance? As I told, the input impedance play a significant role when you want to talk about input filter design, because most of the DC-DC converter, suppose if you go for, let us say, automotive application, that means if you go for automotive application, automotive space application that we have discussed, right, these applications. So, this application you need to meet certain stringent EMI constraint. That means you need to consider one input filter, which is we call it as a EMI filter. EMI filter. So, when such EMI filter is considered, then it becomes very important to justify the stability of the converter with the EMI filter, and then in order to justify stability, we need to get the transfer function of the EMI filter, and we need to get the input impedance of the converter, and then using Middlebrook extra element theorem, we can justify the stability of the converter along with the input filter. Okay? So, the input filter play a significant role when we consider the input impedance play a significant role if you want to design a stable power converter with an input filter. But suppose if your input filter bandwidth is low, then your control bandwidth will also get reduced because you have a high inertia input filter at your input side. So, you cannot sleeve up the inductor current fast. So, as a result, you have to slow down the converter, right. Otherwise, what will happen if you want to speed up, it will become unstable because your input filter has a low bandwidth and your converter high bandwidth. So, it cannot, because in a cascaded system, the overall bandwidth will be limited by the worst case bandwidth, right. So, that thing also we have discussed. Another aspect is that if we want to consider, so it is a buck converter, you can do the same thing for a boost converter. So, suppose if you talk about a PV panel, that means you talk about a PV panel, solar panel, and you have connected a boost converter, right, a boost converter, okay, and maybe you have a resistive load at the output side. So, then it is very important to find out what is the input impedance of the boost converter, right. That means it is important to find input impedance, and since the PV panel, the changes, the dynamics of the PV panel changes very slowly, because it's in the order of second or even minutes or even hours. So, we will consider the low frequency behavior of the input impedance, and which can be shown at low frequency. The input impedance will be simply at low frequency alpha R by d square, and we know what is alpha. It is, that means it will be R plus R equivalent divided by d square. So, this is a low frequency behavior. This is particularly important for that maximum power point tracking and such kind of application, where we need to take into account the impedance of the source as well, because you need to match, because you can apply the maximum power transfer theorem. So, if you can derive the input impedance, and then if you considering the resistance, then you need to find out at what point should you operate to extract the maximum power. The output impedance, we have already discussed the output impedance of an ideal buck converter. If you consider a practical buck converter, so we know that output impedance will look like the inductor capacitor resistance will be in parallel, and I discuss at very low frequency this inductor will behave like a short circuit. That means at low frequency, so if you say the low frequency behavior, it will be like Re in parallel with resistance R, right, and that will be connected to your external current. Okay. So, external current. Okay. That means in this case the output impedance can be simply Re parallel R, which is nothing but R into Re by R plus Re, and this will be equal to Re if Re is very, very small, and this can be shown that it is almost equal to Re if R is very, very greater than Re, right. So, that means this is the limit of the output impedance at low frequency, which is coming due to the DCR. That means Re is nothing but what? Our Re is nothing but DCR plus R on. So, you have to suitably select the switches with low RDS on, low DCR, so that the DC impedance low frequency can be smaller. But again, this is an open loop characteristic. Even if you have a finite the low frequency resistance like effect, by means of closed loop control, if you put an integral action, you can achieve very tightly regulated output voltage. So, this will not cause problem, but this will cause a problem in your efficiency, because we have discussed the efficiency strongly depends on this Re. If Re is high, then efficiency will degrade, particularly when the load current increases, and you will end up with something like this kind of profile. That means you will get something like this kind of profile. As you increase load current, then your efficiency will fall, right. And if your Re is higher and higher, so this profile will tend to even more sharper. Okay, so you need to choose, that means, and if you have a very good Re, you may get something like this kind of curve, almost flat curve. Okay. So, this Re can be calculated, and this will look like, that means as I said that your poles are common, and we have already discussed the pole. What are the poles? So, here delta S 1 plus S by omega 0 plus S square by, this is a natural frequency, right. Yes, so those we have discussed, and you have two additional, you have two 0. One 0 is due to the ESR. So, the ESR 0 is due to the capacitor, and the other 0 is coming due to the inductor, that equivalent. Okay. Even if you take an ideal, like if there is no ESR is very low, so this 0 will come into picture. So, what is the significance of output impedance? Output impedance play a significant role in your load transient response. So, if you take an DC-DC converter, idea like a open loop DC-DC converter, you will see if you want to get at steady state, suppose you apply a load step transient of delta I0, then you will find there is a DC drop, you can say a drop voltage which will be minus of Re equivalent by alpha into delta I0. That means this drop is coming due to this particular branch and along with this branch. Okay. So, this drop, if there is no parasitic resistance, then there will be no drop. That means, if you take two steady state current, that means if I consider, let us say your load current was here, there is, I am talking about a DC-DC converter, the load current is here, suddenly you have, there is a load transient, it has gone up. Now, if you take the profile of the output voltage was like this. Okay. So, sorry, I am talking about the output voltage. So, if we take, so this is my load current I0 plus delta I0 and this is your I0. Now, I want to draw another graph. So, I want to draw below another graph here and this is my V0. Okay. So, what I want to do here, if I extend this, so my output voltage was like this, suddenly there is a transient effect, but it will get settled somewhere here. So, this difference is, we call it as a drop delta, or I will say, so this is nothing but, so this quantity is, this drop is nothing but this drop, this is a load step transient. Okay. But if there is no Re, then it will come back again to this point if there is no Re, but this is not the case for a practical converter. So, there will be some drop, right. Again, the transient behavior, that means the frequency dependent term will shape the undershoot, like if there is an overshoot, undershoot or such kind of behavior, how far, like what will be the maximum, like undershoot that can arise under load step input voltage. So, those will be decided by this transfer function, frequency dependent term. And the high frequency, there will be jump here and this jump will be ESR, because at very high frequency this will be open circuited, this is a short circuited and this RC will come. So, RC will create a drop, so very high frequency. So, you will get a jump, that means every load transient will have a jump and this jump will be RC into delta I0, that step, and this is generally negative. Positive load step to negative jump. Similarly, we can find out audio susceptibility for a practical converter and we can get all the transfer function. And what is the significance? I told you that audio susceptibility, if there is any disturbance, particularly why the term audio susceptibility come, because if there is any audible noise present in the supply source, which can be, because it may so happen that suppose you are talking about a battery of a, let us say your mobile phone, where the multiple converters are connected, that means this is your battery, I am talking about a battery. So, battery has a positive terminal, negative terminal. Now, with this positive terminal, you have like a DC-DC 1, another like a DC-DC 2 like this, and though there is a small input filter, but if you go to PMIC like a power management circuit, it will be very hard to put large capacitor. So, there will be a small input cap will be there for each converter, because the power density is a concern. Now, suppose if there will be input current, like it is drawing by this converter. Suppose for some reason one of the converter undergoes subharmonic instability kind of behavior. So, that will be reflected to the battery and this battery is connected to the other converter. So, this can propagate through the converter. So, if you have a very good audio susceptibility, it will be rejected at the output end. Okay. So, that is why it plays a significant role. Output impedance we know how to find out, and we already have discussed. Sorry, this is a control to output transfer function. We have already discussed. So, in the control to output transfer function, we have 1 0 here. This is due to the ESR. So, we generally write this like this, like ESR 0. So, this 0 is basically, this can be also written as 1 plus S by omega ESR. So, ESR 0, and this ESR 0, if the ESR is low, it will go very high frequency. So, that effect is negligible, but it will be primarily dominated by this 2 poles, right. And we will discuss in the next lecture, effect of poles and zeros. Suppose if you incorporate 1 0 into a system, then how is it going to affect the response? That also we are going to discuss. But I can tell you, if you take a transfer function g of s, which let us say and you are giving one input u and this has an output y 1, and I am taking another transfer function which is g, this is g1, this is g2, suppose this is y2, and you are using the same input, right. If g1s is something like whatever you have studied in control system, s square plus 2 zeta omega n s plus omega n square, and if we take g2s to be g1s multiplied by some s plus omega z 1 0, then if you take the time domain response of y1 t, we can obtain, because the time domain response will be what? The time domain response, if we take the initial condition to be 0, it is the Laplace inverse of g1s, it is unit step response. So, we are talking about unit step response, right. Then you can find out, that means for a given unit step, then you will find out y of 2 top t is nothing but y of t plus 1 by omega z into dy 1 of t by dt. So, this is the extra term that is coming due to the 0. So, this is extra term coming, this extra term is coming due to the 0, and if this 0, that means if omega z is very high, that means 1 far away, or it is very I would say omega n, rather I will say omega n, because this is a relative term, right. So, if you take omega n, then this has negligible effect, it is negligible effect, But if it is coming close to omega n, then this will have significant effect, and this will add some derivative action. Okay, so, this can affect the response of the system. Now, if you go for a boost converter, we have already discussed about the AC equivalent, like a equivalent circuit model. So, you can get the AC equivalent circuit model of a boost converter, and we can find out the input impedance, the same method. And as I told, this input impedance of a boost converter is very important, particularly when you are talking about like a MPPT, like a solar panel, where at low frequency this input impedance will simply become 1 minus d whole square by r. In this case, it looks like, right, because this is now connected to a solar panel. So, you have to match the impedance, right, for maximum power extraction. Okay, so, this also play a significant role when you want to consider input filter and so on. So, output impedance, the same method you can apply, and you will find the output impedance something similar, but in this case the poles here will have a duty ratio dependence, which was not there earlier. In buck converter, the poles does not depend on the duty ratio, but in boost it also depends on. That means the Q factor, the natural frequency Q factor, they also depends on duty ratio in a boost converter. That is why if you change the duty ratio, the whole pole location will also get shifted, and it becomes very difficult to compensate for a wide range of deterioration. You can also derive the audio susceptibility by the same method and you will get the audio susceptibility expression. So, I am not going to separately discuss because this is all standard, we have already discussed. And if you want to derive the control to output transfer function for a boost converter, then if you go step by step that how to V0 and V, it requires few more steps. It is not very straightforward like a buck converter, and if you follow those steps and substitute the intermediate variable, then you will get the control to output transfer function a boost converter like this. And as I said, it has two poles, that means it has two stable poles, but duty ratio dependent, duty ratio and load dependent. In case of buck converter, it was load dependent, but it was not duty ratio dependent, the pole location, but here it is. And it has one right half plane 0, that is called RHP 0. That means it is nothing but right half plane 0. Right half plane 0, and this actually makes, because we have discussed just the previous case, if we take a G1 of S, which is, let us say in this case particularly, suppose this GVD, let us say this GVD is equal to G1 S into 1 minus S by omega RHP, suppose. So, G1 is nothing but let us say V in D dash square SL by R plus S square by into LC. So, this is the transfer function where we have only two stable poles, there is no 0, but GVD S is nothing but G1 S into 1 minus S by omega RHP. And what is omega RHP? It is nothing but R 1 minus D whole square by L, because it is coming from this expression. We are writing S by omega RHP, right, in this form. That means, if we write y of 1 S, y of t in time domain, it is the inverse Laplace of, you can get G1 of S by S. So, we are talking about unit step response. And YGVD t is nothing but y1 of t minus 1 by omega RHP, this factor into dy1 of t by dt. And you see, we have discussed that if this quantity is large, that means if omega RHP is in one case is very greater than omega natural frequency, where the natural frequency can be represented, because we can take the duty ratios common. So, natural frequency, let us say omega 0 is 1 minus d by square root of LC. If we take, this is the natural frequency, is very large, then this effect is negligible. But if it is comes close to the axis, it is severe, and because of the negative sign, it introduces an inverse response. And in the next presentation, we will discuss with MATLAB case study that how it is going to affect. Okay? But in a boost converter, this right up plane 0 location varies with the load current, it varies with the duty ratio. And of course, in a boost converter it is better to choose a smaller inductor, so that this, because our objective to push this RH0 as far right hand side as possible, so that this effect can be reduced. Okay? But load and duty ratio is something not in our hand, it will change. So that is why it is very difficult to design a boost converter for a wide range of load current and duty ratio using a fixed frequency for a fixed gain controller. So if you go for digital control and if you can adjust the gain, then you can optimize the performance. Otherwise, if you design based on worst case scenario, then you cannot design a converter compensator for a wide load current and duty ratio range, because that will simply kill your performance significantly and nobody will buy it. So, small signal transfer function of a boost converter, we have discussed different input impedance, output impedance, audio susceptibility, control to output transfer function, and we have discussed their significance. Same thing is applicable for boost converter also. So, in summary, we have discussed small signal model of an ideal and practical DC-DC converter. We have derived input output impedances of DC-DC converter with practical parasitic. We have derived control to output transfer function, audio susceptibility. We have understood some practical limit on output impedance and control bandwidth, because in case of right half plane 0, your control bandwidth can be limited because of the inverse response of the right half plane 0. And in case of output impedance, the practical parasitic can put a limit both for ESR drop and also your DC value, which can be anticipated by means of closed loop control, but still efficiency will degrade. With this, I want to finish it here. Thank you very much.